To map how information moves across a network, we have to look past the hardware and track the mechanical journey of the data itself. Network engineers use the Open Systems Interconnection, or OSI architecture, to trace this process. The OSI stack functions as a mechanical, step-by-step encapsulation pipeline. This data encapsulation diagram shows the path. We will track a single payload top-down through node A's stack, observe its transformation into physical energy, and follow it to its reconstruction at node B. Understanding this downward and upward directional flow provides the foundational logic required to isolate and diagnose network failures. This application layer chart shows the topmost entry point. It provides networking services to the user by identifying the required processes via port numbers, utilizing ranges from 0 to 65,535. Moving down, the presentation layer standardizes data formats so systems can communicate, agreeing on standards like ASCII or JPEG. Core tasks here are operational: encoding, encrypting, and compressing data before the transport phase. The connection is formalized at the session layer. It establishes, maintains, and terminates the connection using a dedicated session ID, which is required for running processes like remote procedure calls or SQL queries. Notice the protocol data unit, or PDU, state across this phase. Through these three upper layers, the unit remains structurally intact and is recognized simply as data. These top three layers act as a software-side staging ground. At this point, no network transmission logic has been applied to the payload. The payload drops into the transport layer. As the chart states, this is the heart of the architecture, handling end-to-end connectivity. It executes critical logistical tasks, multiplexing streams, error correction, and applying flow control so receiving machines aren't overwhelmed. To prepare the data for the wire, the system performs a structural alteration. The large block of raw data is mathematically chopped into smaller, sequentially numbered units. On the master diagram, this creates the first PDU state change. The data is now formally categorized as a segment. Without this segmentation at the transport layer, a large file transfer would monopolize the physical bandwidth and stall the rest of the network. The segment drops to the network layer, where the primary objective shifts to calculating the best path to the destination. This uses logical addressing. Hardware like routers use specific routing protocols to read IP addresses and navigate the topology. To survive routing across the open internet, an IP header is wrapped around the segment. This encapsulation changes the unit state to a packet. Next, the packet is pushed down to the data link layer. It's divided into two operational halves: logical link control and media access control. The AAMC sublayer relies on a permanent 48-bit hexadecimal identifier hard-coded into hardware for local routing. Returning to the pipeline, the packet is encapsulated inside this MAC data, forming the next defined structure, a frame. The division of labor is strictly defined. The network layer handles the global logical map, while the data link layer executes the physical point-to-point local hops. The frame drops to the physical layer, the domain of pure hardware. Here, structured data is stripped of its software identity, converted into binary electrical pulses over copper cable, or flashes of light through fiber optics. The architecture of the frame dissolves, serializing into the rawest PDU state, a stream of bits. Look at the glass fibers inside this cable. The hardware operating at this level processes this energy blindly, with no awareness of the data's meaning. The physical layer applies no logic regarding IP addresses or routing. Its purpose is moving physical energy across a gap. In the full pipeline view, the serialized bits cross the physical medium from node A and arrive at node B. At the destination node, the process runs in reverse. This is de-encapsulation, where the data strips off its structural shells as it travels upward. Data link verifies the MACADAS, network checks the IP, transport reassembles the segments, and presentation decrypts the payload. Forcing all traffic through this identical sequence ensures interoperability. It is why a router built by one manufacturer can interpret a packet created by a different company's server. Each layer only processes the specific header intended for its level, leaving the rest of the payload untouched. This allows the data link layer to change, moving from a copper wire to a fiber optic cable, without the application layer ever needing to adjust its logic, ensuring that hardware-level changes or failures remain isolated.